Welcome to the Problemos channel, Season 2, Episode 14, the episode which I titled Geometry in Fake Coin Detection Problems, because in this episode we will be discussing the possible solutions of the mathematical problem S2M16. Before we do that, however, as a traditional friendly reminder, if you are joining our channel mid-season, then first of all, welcome to the channel. Thank you for your vote of confidence. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To and watch that episode in its entirety and follow all the instructions given in that episode, because in that episode we describe and motivate everything that we do on this channel. As a refresher, in the challenge S2M16, we were asked to put together a fake coin detection problem that admits a geometric solution. In other words, in the mathematical problem S2M16, we are expected to put together everything that we know about the space-time problem-solving approach with everything that we know about the process of searching for a solution of a fake coin detection problem, and without getting too involved and too complicated, using simple and manageable numbers, construct at least one fake coin detection problem that admits at least one geometric solution, and in a more global sense, the solution or a problem with the geometric solution that you can come up with doesn't really have to be precisely about the fake coin detection process. It can be fairly related to it. Some people think algebraically, formulaically, and symbolically better in some sense than they think spatially, visually, and geometrically, and the other way around. There are some people who think spatially, visually, and geometrically better in some sense than they think symbolically, formulaically, and algebraically. There are also some people who think in a way that is smudged somehow between these two extremes, and there are people out there who think in a way that is fairly well balanced between these two extremes. If you think that you are a person who thinks better in one way and not in the other, we still recommend that you keep the other way of thinking on a leash that is not too long, because your attempt to learn how to think the other way in another mode, so to speak, will only make you a better and more well-rounded mathematical thinker, because historically we know that the proverbial geometry and the proverbial algebra enjoyed a mutually beneficial relationship that complemented each other. For example, Albert Einstein used to say that geometry is perhaps the earliest branch of physics. And besides the modern discipline that we call these days analytic geometry, which is a happy marriage between the proverbial algebra and the proverbial geometry, there exists another grown-up layer of mathematics that brings this idea front and center, and that layer is called geometric algebra, which perhaps takes its roots in the works of the ancient Greek mathematician Diophantus, who knew how to solve not only fairly sophisticated linear, quadratic, and cubic equations over the set of integers, but he also knew how to solve the systems of quadratic and cubic equations over the integers. And the way he did it is he came up with a fairly clever and sophisticated, even by modern standards, substitutions. And again, to the best of my knowledge, in the Western civilization, it was Isaac Newton who was the first one to realize that the very and quite complex substitutions that Diophantus used in his work have a fairly straightforward geometric interpretation, and thus, in some sense, again, how the modern layer of mathematics, to which we refer now as algebraic geometry, was born. For example, the moment we try to rationalize the points on a, let's say, unit origin-centered circle, then one way to do so is to find, for example, one rational point on the periphery of that circle and construct a second of that circle that will also establish a certain relationship between the points on the periphery of the origin-centered unit circle and, for example, the subset of real numbers right here between 0 and 1. And once we step up our work and move from, for example, a circle to an ellipse, a thing that looks like so, for example, then eventually in our work, related work, we will come across the notion of a tangent to an ellipse. Either way, anytime any problem in any vaguely defined layer of mathematics admits two fairly distinct types of solutions, an algebraic solution and a geometric solution, we should always seize on that opportunity and construct both such solutions, because these solutions will shine two different rays of light on one and the same matter and will thus help us better understand the phenomenon at hand. And that is precisely what we will do in this episode by constructing geometric or geometrically driven non-adaptive solutions of fake coin detection problems. In this episode, I will solve 3 fake coin detection problems geometrically, and out of these 3 problems, 2 problems will be familiar to us, and the wording of the third problem will be mine. But once you understand what is going on in that third problem, I'm pretty sure that you will be able to come up with a wording of that problem of your own, and that wording will be even more beautiful and elegant than mine. As such, even though in the mathematical problem S2E14 we are asked to construct at least one problem that admits at least one geometric solution, we will discuss the geometric solutions of 3 fake coin detection problems. The first problem that we will solve geometrically will be the standard 9-coin problem, in which we are given 9 visually indistinguishable coins. Exactly one of these coins is known to be fake, and it is known ahead of time that that fake coin weighs detectably more than a genuine coin. We refer to that coin as fake and heavy, as designated by the letter H over here in parentheses. And we already understand very well how we can generate a non-adaptive solution of that problem based on an adaptive solution of that problem. And we also understand very well how to generate an adaptive solution of this 9-coin problem. We represent that adaptive solution with a graph theoretic object known as a ternary tree. This is a graph that has no cycles and in which there exists precisely and exactly one unique path between any 2 nodes of the tree. And since this tree is ternary, it means that each and every node of the tree has no more than 3 descendants. We represent each weighing with the hollow circle shown over here in white, and the bottom or leaf nodes over here, for your convenience, I depicted in yellow. I'm not sure if you can see it, but that was my intention. The leaf nodes are yellow. The nodes that represent each possible weighing are shown as hollow white circles here and here. We also sprinkle the letters L for left pen going down, B for pen's balance, and R for right pen going down along the legs of each path that originates at the root of the ternary tree that represents the very first weighing in this problem. And we thus generate a complete set of 2 permutations of 3 distinct items, the letters L, R, B, each of which is available in an infinite supply. We know that combinatorially deduced formula for this is n to the power of k. In our case, n is 3, k is 2 positions representing 2 weighings. 3 squared is 9. And if we encode each and every coin with the corresponding 2 permutation of the letters L, R, B, then we will generate a unique path for every coin in our set, or we will generate a unique fate, so to speak. And we understand that no 2 coins can have a duplicate or one and the same fate, because then we will not be able to distinguish or tell these fake coins apart. Each specific coin is associated with its own unique path. Thus, we create this translation table shown over here. For the first weighing, for example, we can put the coins named 1, 2, 3 on the left pan, the coins named 7, 8, 9 on the right pan. We can keep the coins named 4, 5, 6 on the table. Depending on the outcome, we either, for the weighing number 2, weigh the coin named 1 against the coin named 3, as shown over here, or we weigh the coin named 4 against the coin named 6, as shown over here, or we weigh the coin named 7 against the coin named 9, as shown on the far right on your screen. And depending on the outcome, we generate all the leaf nodes, which account for all 9 coins. Over here, just for our shared amusement, I numbered the coins 1, 2, 3, 4, 5, 6, 7, 8, 9. But we understand that if there is no other hidden or parallel agenda, if we just solve this problem in vacuum, that then these names are absolutely irrelevant, and the first-class citizens in this adaptive solution of the fake coin detection problem are precisely the fates or the unique paths. Now that we know how to generate an adaptive solution and represent that solution with a ternary tree, we can write down a non-adaptive solution shown over here at the bottom on the right of your screen. This non-adaptive solution represents a series of steps that can be written on paper ahead of time before even the first weighing commences. We can give that set of steps to a person who has absolutely no clue what is going on and what he or she is doing. As long as that person follows our instructions and writes down the result, the outcome of each weighing, then the person hands us this 2 permutation. We'll look at this 2 permutation, and with absolute certainty we announce, aha, this coin is fake and heavy. For example, the person to whom we give the instructions will put the coins named 1, 2, 3 on the left pan, the coins named 7, 8, 9 on the right pan. The person will keep the coins named 4, 5, 6 on the table, perform the first weighing, and write down the result of that weighing. Let's say the result of the first weighing was, let's say, the pens balanced, for example, just for kicks, the pens balanced. Then, regardless of the outcome of this first weighing, the person mechanically or blindly, in some sense, will take the coins named 1, 4, 7, put them on the left pan. Then the person will put the coins named 3, 6, 9 on the left pan. On the right pan. That person will keep the coins named 2, 5, 8 on the table, perform the weighing, observe the result, write this result down, pick your favorite. With the live audience, I would ask, okay, what's your favorite letter over here? Let's say the pens went right. So here again, don't forget that you can keep track of these directions in any which way you like. Most people will do it left to right, as I explained before, because 9 to 5 for 30 years I'm writing C++ code, and the bits in the byte are numbered right to left. I keep track of my directions right to left. For example, here you can see balanced right corresponds to this path, balanced then right. Consequently, in the same way, we interpret the results of the non-adaptive solution that were given to us by the person in the same way, right to left, BR. We go to our translation table, boom, the fate or the path, the unique path, the unique 2 permutation is BR. We find it here, BR, bam, the coin number 6 is fake and heavy. This is all fine and dandy. We understand very well how that works. Quite frankly, we're bored at this point, but all of a sudden this guy named Roman walks in and says, listen guys, in addition to this mostly algebraic or symbolic solution depicted over here and non-adaptive solution of a fake coin detection problem, it is possible to generate that same solution shown over here, not algebraically through two permutations in some sense, but geometrically. At this point, we think, aha, what is going on? On the one hand, with the ternary tree, we have a nice and beautiful visual representation of the combinatorial object known as two permutation of three distinct items, each of which is available in an infinite supply. So how on earth let's say, Euclidean geometry can be dovetailed into this and produce essentially the same or equivalent solution? Well, let's concentrate on that number right here. 3, the number of coins, the number of paths, the number of possible two permutations, which we talked about, is what? Is 9. And what is 9? 9 is a perfect square. So let us concentrate on this guy right here. Most people on the face of this planet, once they hear the words blah blah squared, what type of an association they may have? Well, first of all, most people on the face of this planet have no mathematical education. They probably and most likely do not know that in this shape, blah blah squared, they're dealing with an algebraic square. But despite the fact that most people on the face of this planet do not have any specialized mathematical education, it is highly likely that the first association that they will have the moment they hear the words blah blah squared will be what? Precisely, will be a geometric square. Let's pretend that this is a geometric square, and this is the first step in the right direction. And in the next segment, we will investigate how this idea can be converted into geometric solution of the same problem. Now that we made an important step towards our miniature discovery for moving from an algebraic square toward a geometric square, what will happen next in real time will depend on your level of mathematical maturity, your overall level of mathematical knowledge, and your level of problem-solving experience. Those of our viewers who are familiar with the notion of a Cartesian product or a multiplication table of a group will know what will happen next. But even if you do not know what a Cartesian product is, even if you do not know what a multiplication table of a group is, eventually you will realize that in order to repackage the 9 units of information shown over here, or in order to port or export our ternary tree into a square, we have to be reasonably systematic. Once we make our next miniature discovery, we will realize that we do not really have to be that systematic, but for the purpose of the immediate step, let's say we want to be reasonably systematic, and we want to package or repackage the given 9 units of information into a square. How can we do that? Well, if we break our geometric square into, let's say, 3 columns like so, and 3 rows like so, then over each column we can write the letters, for example, L, B, R. Again, that order doesn't really matter. We can hash these guys any which way we like, but again, for the purposes of being systematic, let's say we named our rows like so, LBR, and we named our columns LBR, and the idea is to pack this 9 units of information into this square in a systematic way. And for example, in the theory of groups, when it comes to constructing a multiplication table of a group, the convention that I'm about to tell you is arbitrary, but it's quite popular. And for the purposes of forming the so-called group product, it is customary to take the left factor from the corresponding row and the right factor from the corresponding column. Here we do not have any group theoretic products, but in some sense, by analogy, we fill out each square with the fates of our points in pretty much the same way, and we write the left letter over here in that square, which is taken from the row header, and we write the right letter that is taken from the corresponding column header. So here we'll write the letters LL. Here's our two permutation LL. Here this guy is shown over here, and we move on in the same fashion over here in this square. What do we write? The left letter comes from the row header L. The right letter comes from the column header B. Here we will have LR. So for example, to give you guys a hint, we write the right letter in our square taking it from the column header, and we write the left letter by taking it from the row header like so. Let's fill out this row. So the left letter will be B because it comes from the row header. The right letter will be L. Here we will have B, B. Again, all these fates can be found in our translation table. For example, LB, where is LB? LB is right here. Then we have LR, LR is right here, and so on. So here we will have B on the left because it comes from the row header, and R on the right because it comes from the column header. And the bottom row will look as follows: R, L, R, B, and R, R. And again, we have in some sense to be possibly quite pedantic about it. We have a one-to-one correspondence, a bijection between the two permutations shown over here and the two permutations that live in our table. And again, you do not need to know about Cartesian product. You do not need to know about a multiplication table of a group. But if, let's say, you want to explain how you filled out this square to your grandfather or your grandmother, or if you want to explain it to a wall, what kind of keyword will you pronounce in this case? Well, the keyword that you will pronounce in this case is the following. Every square in our table, sits at the intersection, and that is the keyword, intersection of the proverbial X row shown over here and the proverbial Y column shown over here. Bam, this is our guy. And that means that each and every square in our 3x3 table sits also at the intersection of the corresponding row and column. It can be portrayed right here. And what we have now is 9 points, each of which corresponds to an intersection of two straight lines which are not parallel. And this is precisely where the space-time problem-solving approach dovetails into the process of the discovery of a geometrically driven non-adaptive solution of this fake coin detection problem. Recall that no problem-solving algorithm, no problem-solving approach provides any algorithmic guidance to the process of searching for a solution of a problem. The space-time problem-solving approach is no exception. It doesn't provide any hard algorithmic guidance for searching for a solution of a problem, but that problem-solving approach says that under most circumstances, between the main components of the problem at hand, there may exist interesting four pairings of these components over space and time. And the time in the space-time problem-solving approach is pretty much what it is, but the word space in that approach is somewhat flexible or wide because it can be literally anything that we need it to be or literally anything that we want it to be. Recall that in the end of the previous episode, I gave you a hint of looking at two intersecting straight lines. I kept this hint over here. You may know, for example, so Y is in this case a straight line can be correlated to a space in our problem from this space-time problem-solving approach. Well, there is actually quite a lot going on with, for example, a fixed straight line in a fixed plane. That is, to every fixed straight line, let's say we'll fix it by giving it a name, L, to every fixed straight line in every fixed plane, there corresponds an infinite and not commutative group of so-called congruence motions of a straight line, or a group of self-coincidences of a straight line. For example, what are the elements in this group? Well, the elements in this group are two popular geometric transformations, and the binary group operation in this case is composition of these two popular geometric transformations. Which are they? Well, the first one is, let me designate it, for example, right here, is the parallel translation. I'll designate parallel translation with the letter T for translate along the vector A, designated over here, vector A, that is parallel to that straight line L. And what is the most obvious low-hanging fruit candidate for such a vector? Exactly, it could be any vector that sits precisely on that straight line. For example, this way, we can designate this guy as a vector. So in this sense, this specific parallel translation of the straight line, fixed straight line in the fixed plane, can be referred to in less pedantic language as gliding of the straight line along itself. In other words, this specific parallel translation can be looked at as shifting the given straight line to the left, for example, or to the right. That is one element of that group. The other element of the group will be a rotation. I'll designate it with the letter R by technically, let's say, k pi radians over any point P that belongs to that straight line L. For example, let's say we take this point P right here, this point, rotate that straight line by, let's say, pi radians clockwise or pi radians counterclockwise, or in general k pi, where again pedantically k varies as 1, 2, 3, and so on. That will be another element of that group. If we glue all these elements of this group with the binary operation of composition, we get an infinite, not commutative group of congruence motions of a straight line. So actually quite a bit is going on just with one straight line. And for example, these guys, these elements form a subgroup of this group, and so on. So now that we understand that each straight line, for example, here in this case, can be quite useful and can be interpreted as a space that we need, then in the next segment, we will convert that observation into a purely geometric solution of non-adaptive solution of a fake coin detection problem. Before we move on, one small wrinkle. The set of congruence motions of the fixed straight line and the fixed plane that I discussed in the previous episode, designated here with the letter R for rotations, is really an infinite set because the factor k in k pi varies over all the integers, the whole number 0, and then plus minus 1, plus minus 2, plus minus 3. And the popular representative of this infinite set is the positive value of pi, that in mathematics is usually associated with the counterclockwise notion. In any case, so far we managed to generate a number of good thoughts and good ideas. We took the standard 9-point problem. We generated an adaptive solution of that problem. We represented that adaptive solution with the ternary tree. Then we generated the complete set of the respective two permutations or unique fates or unique paths for each coin. Then we wrote down and generated the corresponding non-adaptive solution of the problem. Then we generated a happy thought of converting or exporting our ternary tree, so to speak, and folding the tree into a square. Then we realized that each and every smaller square in that 3x3 table represents our coin, and that square sits at the intersection of the corresponding two distinct, not parallel straight lines. And now the question is, how do we convert all these good observations into an actionable and tactical geometric non-adaptive solution of the 9-point problems? Well, if we think about it, then we will realize that we do not really have to be that strict and that pedantic about our straight lines to be strict verticals and strict horizontals. We can be somewhat much more looser. But if the three interesting spaces with the actual set of pen scales were what? The space of the left pen, the space of the right pen, the space known as the table, or in other words, the space that's neither the left pen nor the right pen. Then in the geometric solution, what is the corresponding model of these spaces? Well, these models are shown over here. These models are straight lines. One straight line corresponds to a left pen, one straight line corresponds to a right pen, the right pen, and one straight line corresponds to the table, which we designate with the letter B. Consequently, again, for demonstration purposes, our geometric non-adaptive solution of the 9-point problem will look as follows. First, we pick a set of any three distinct parallel straight lines, and the spacing between them doesn't have to be, again, the same. The spacing can be anything we want. Let's say for demonstration purposes, I pick this straight line right here. I want to give it a reasonable spacing like so, and another straight line like this one. 1, 2, 3. Again, spacing doesn't have to be the same, but most people will probably draw these straight lines so the spacing is the same. It doesn't have to be. Then we generate the second set of three distinct straight parallel lines. And these straight lines have to only follow one constraint. They have to intersect each and every of these straight lines from the first set. So let's say for demonstration purposes again, I intersect these guys like so. So this will be the straight line number 1. This will be the straight line number 2. Not very parallel, but anyway, and that will be the straight line number 3. So let me just designate these guys more like so. See, it doesn't have to be pretty, and the spacing doesn't have to be the same. It could be in some way haphazard enough, but fundamentally, the two sets of three distinct parallel straight lines each must, that's our only requirement, intersect over 9 distinct points in the parent, let's say, Euclidean plane. This point, this point, this point, this point, this point, 6, 7, 8, 9. Bingo, we have our points, and these geometric points are the models of our coins. Consequently, how do we design, how do we use the geometry of what we generated so far in order to construct a non-adaptive solution of this problem? Well, for the weighing number 1, we simply have to pick any two distinct parallel straight lines. Again, which ones out of these 9 we pick for weighing number 1, it doesn't really matter if we don't have any other hidden agenda for the solution of this problem. We can, for weighing number 1, we can pick, for example, this one in this straight line, this and this. We can pick which one, this one and this one, this one and this one, or this one and this one, and so on. And for demonstration purposes, again, let's say I will pick, I don't know, let's say this one. I'll pick this straight line right here, this guy, and this guy right here. I'll pick this one. So these two straight lines will represent the spaces to which we refer the pens in our actual pen scale setting. So this will be, I'll mark it weighing number 1. This will be weighing number 1. Here, weighing number 1. And again, which straight line we pick to represent the left pen and which straight line we pick to represent the right pen, it doesn't matter. Either one can do. For demonstration purposes, let's say I pick this straight line to represent the left pen. I'll designate it with the letter L, and I'll consequently we will make this straight line represent the right pen with the letter R. I'm sorry, I'll erase this guy, letter R. And what does that mean? Well, that means that in this case, the green chalk with green chalk, we will designate the space called the table. It will be balanced and it will be for weighing number 1. And what do we do next? Next, we roll through each chosen straight line, and that straight line will house exactly 3 geometric points, each of which will correspond to our coins. And we name each such point, geometric point, with the corresponding pen that this straight line is associated with in the proper position. So in the rightmost position for me, for you, if you do it the other way, in your leftmost position, you will write for this point, you will write the letter L. Here you will write the letter L. Here you will write the letter L. Next, we roll, let's say, through these 3 points. These points represent what? They represent the table space, so we write B for balance here, B for balance here, B for balance here. Beautiful. And what do we do here? We roll through the remaining 3 points, and for each one, we write what? Let's say I write it over here. Let me erase this to not confuse us. So let's say this point right here will be R. This point will be R also. And let's say this point, I'll mark it over here just to be consistent, R. So now we marked all the points with the corresponding pens or the table with the letter B, depending on our choice. And we need to understand now, before we move on, that whenever we execute an actual weighing in the geometric context, what does that mean? That means that the outcome of that specific weighing will identify what? It will identify precisely one straight line out of these 3. For example, if the left pen went down, we know that this straight line is it, the primary suspect. If the right pen down as a result of the first weighing, it means that that straight line is our primary suspect. If neither pens went down and the pens balance corresponding to this outcome, then this straight line will become it or our main suspect. Consequently, what do we do next? Well, because there are only 2 weighings in the 9-coin problem, for our next weighing, for the weighing number 2, we have to pick the next 2 distinct parallel straight lines. And here we need to understand, can we pick any one of the straight lines that were chosen before? Yes or no? And most importantly, why? Think about it. The answer is actually no. And as a proof, let's assume for a moment, setting up a contradiction, that we picked, for example, this straight line and then this straight line for weighing number 2. Whether we choose this line to represent the right pen again or the left pen, it does not matter, because according to our geometric algorithm, we roll through all the points that sit on that straight line. And in the second position, we mark the corresponding letter. For example, here, if we represent this straight line, choose this straight line to represent the right pen in the weighing number 2, there will be letters R, R, R. If we switch things around and we choose to represent the left pen with this straight line for the weighing number 2, it will be letters L, L, L. It doesn't matter. But what's important? The important thing here is that we will have 3 duplicate or not distinct fates or paths, and this is not allowed. This is a contradiction. Recall that in our translation table over here and in the mechanics of how we generated this paths or fates, no 2 coins can possibly have the same fate or the same path, because otherwise we cannot tell them apart which one is fake and which one is not. Consequently, for the second weighing in our geometric solution, we need to pick any 2 other straight parallel lines that were not chosen before. Again, here for demonstration purposes, we can pick, for example, this one and this one, this one and this one, or this one and this one. Let's say, just for kicks, I'll pick this one. I'll pick this straight line and this straight line for the weighing number 2. I'll write it down, weighing number 2, weighing number 2. Consequently, which one? This one also will be weighing number 2. I will use, for example, this one. This straight line will represent the left pen. Again, let's say this straight line will represent the right pen. That means that this straight line represents the table marked with the letter B. And what do we do now? Exactly, we roll through the corresponding 3 points that sit on each of the chosen lines and mark the names of these points accordingly. In the second position, for example, for these points, we mark these guys with the letter L. L, L, L. Beautiful. We roll through the points that sit on the straight line, and we mark in the second position the corresponding letter. R, R, R. Awesome. And what do we do next? Well, we roll through these 3 points that sit on this straight line that represents the table, and we mark with the letter B the second position. B, B, and B. Wonderful. And here we have it. Before we finish the explanation of this geometric algorithm, let's see what will happen now. Let us say, for demonstration purposes, that when we executed the weighing number 1, out of these 2 straight lines, for example, the left pen went down, which means that this straight line, actually, let me circle it with the red chalk. Let's say this straight line became a prime suspect, which means that the left pen went down. If that straight line went down, we would circle it, and if neither one, we will circle this one that represents the table. Okay, so now let's say what happens during the second one. Again, let's say for demonstration purposes, neither the right pen nor the left pen went down. That means that as a result of the second weighing, the fake coin was on the table. So this straight line will be our main suspect. We will circle it this way. So now we have 2 straight lines as a result of 2 weighings that are distinct and that are not parallel. And in the Euclidean geometry, what will happen in this case? Well, they will intersect at the unique point. So boom, this guy is the fake and heavy coin. So what do we do now? Well, because for the purposes of generating a non-adaptive solution, we must down our recipe ahead of time before the first weighing commences. So now we understand that all we have to do now is sprinkle our favorite numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 over these 9 points. And the way we do that, again, if there is no hidden or parallel agenda, it can be done in absolutely any which way. For example, again, for demonstration purposes, let's say we name this point, we name it number, let me write it down so we don't have to use number 1. This point will be number 2. This point will be number 3. This guy will be number 4, 5, 6, and let's say this guy is 7, 8, and 9. So we understand it, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, but you can number these points any which way. So now we can write down our non-adaptive solution of this problem that is based purely on the geometric reasoning as explained over here. So for the weighing number 1, these 2 guys, right? 1, 2, 3. On the left pen, what do we put? We put the coins number 1, next 2, next 3. The coins named 1, 2, 3 on the left pen. The right pen is represented by this straight line for weighing number 1. So on the right pen go which coins? 7, 8, and 9. 7, 8, and 9. And the coins that sit, or the points that sit on the straight line represented by the letter B, 4, 5, and 6. So we have 4, 5, and 6. These guys are the bench warmers. They sit it out on the table. For this second, this will be marked. Let's say we mark it with the weighing number 1. We'll mark it here with the weighing number 2. Let's write it down. So the weighing number 2, what goes on the left pen? The coins named 2, 5, 8. So the coins named 2, 5, 8 go onto the left pen. Beautiful. Which coins go onto the right pen for the weighing number 2? The coins named 3, 6, 9. So we write it down here. 3, 6, 9. And which coins sit it out on the table? The coins named 1, 4, 7. So the coins named 1, 4, 7 sit out the weighing number 2 on the table. And this is a non-adaptive solution of the three-coin problem that we generated purely based on the geometric reasoning as explained above. And again, we understand that once the results of this experiment are given to us, perhaps this experiment was carried out by a person who has absolutely no idea what he or she is doing. Once the result is handed to us, again, for example, let's say the pens went left first and then they went right next. So we find LR, the coin named LR. Where is it? This guy, for example. L, the first position in my case, R, the second position, boom. This guy, the coin number 3, is fake and heavy. And now that we understand how the geometrically driven non-adaptive solution of the 9-coin problem is put together, we understand that we can look at the perfect cube, 3 to the third power, and generate a similar geometrically driven non-adaptive solution of the 27-coin problem. Except in this case, when we look, for example, let me write it down over here. Let's say we have, which way? We have 9 points. If we have 9 points in this case like this, again, I'll just make a little sketch over here. What geometric objects do you guys see over here? Let's say this is the top. Let's say, so what's going on here? Well, we can obviously see, the cube happening over here, and this is exactly what we will do in the next segment. Now that we understand how the geometrically driven adaptive solutions of fake coin detection problems come about, we discussed such a path in great detail in the previous segment. Now we'll look at the 27 coin problem, and 27 is a perfect cube, and for many people the words blah 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 cube will bring about an association with a geometric cube. So now I will not go into all these details because you followed all the instructions that we gave on this channel very well, and you kept all the records of the previously solved problems. When you worked on this channel, you can go back to the 27 coin problem, pull up your ternary tree that represents an adaptive solution of that problem. You will see that that tree is 3 stories high. You will see all the possible 27 LRB paths or unique fates of all 27 coins. And now we will cut to the chase by observing that in order to generate a geometrically driven non-adaptive solution of the standard 27 coin problem, what we have to do is literally take, for example, a Rubik's cube, and into each, let's say, unit cube, we put precisely 1 coin. And now that our Rubik's Cube is loaded with 27 coins, with 1 coin per cube, we understand that each weighing will correspond, in this case, not to a straight line, but to a plane technically, or in case of a Rubik's Cube, each such weighing will correspond to 3 layers of the Rubik's Cube that we chose. Let's say, for example, for demonstration purposes, we put all 27 coins into our Rubik's Cube, 1 coin per unit cube. And now for the weighing number 1, we decided to pick, instead of 2 parallel straight lines, this time we pick 2 parallel planes, which again, in general, when you will write out all the solution with all its pedantries, you will pick basically 3 sets of 3 distinct and parallel straight lines. Here, these planes are represented by the layers of the Rubik's Cube. So let's say, for example, for demonstration purposes, for the weighing number 1, we will pick the right face of the cube. For the weighing number 1, and let's say the left face of the Rubik's Cube. For example, if you guys can see it, let's say the cube is positioned this way. For the weighing number 1, we pick this side right here, and for the also weighing number 1 to represent the other pen, we pick this this guy right here, the left face of the cube. Again, the way we assign the letters which will represent the pens in this case, it doesn't really matter. It's completely up to you. I will only highlight the specific mechanics of this geometric solution. So let's say we picked, again, for the weighing number 1, we picked the Rubik's Cube face on the right, on the left. We perform the weighing, and let's say for demonstration purposes, this face was identified as it, which means, for example, if we designate this face of the cube with the letter L, for example, let's say the left pen went down, so this particular face is now a primary suspect. Let's say for the weighing number 2, we picked the front face of the cube and the middle face of the cube. In other words, if this is our cube, then for the weighing number 2, we pick the left face and the center face over here, this guy in the middle, the guy in the middle. Again, the way we assign the letters to this planes in this case, or layers, also does not matter. Let's say you designated this one was left and this, for example, side was right, which means that this was at some point represented by the letter B, and so on. And in this case, this was the layer of the Rubik's Cube that represented the right pen. It doesn't really matter again. So this was the left pen. That was the face of the cube that represents the coin that set it out on the table. So let's say the right pen went down. In this case, it means that between these two layers, or between these two planes, the suspect, the it, is the left face right here, is this guy. I will mark him with blue just for demonstration purposes. This face was identified as it. So far we have identified as the main suspect this plane and this plane right here. Now for the third weighing, for example, we pick the top layer, the top face of the cube, and the bottom again. It doesn't really matter, but let's say we pick these two guys. And again, for demonstration purposes, it doesn't really matter. Let's say the top layer of this three-dimensional cubic cake represents the left pen. This guy represents the bottom layer, represents the right pen. The middle layer represents the balance pen. We all understand how that works. And it so happened that, let's say, the left pen again went down, which means that out of these two planes, or out of these two layers, the top one was identified as it. This guy was identified as it. And now we use the wonderful fact from Euclidean geometry that three distinct, not parallel planes intersect at exactly three distinct, not parallel planes intersect precisely at one point. And in this case, we have the right face shown in red over here, the left face shown in blue over here, and the top face intersect where? They intersect, let me mark it down, for example, with yellow. I will highlight it with this cube right here, this cube right here. This is it. This is our guy. This is the cube that contains the fake coin that is heavy. And again, we do not really have to do this experiment with the Rubik's Cube. Doing this experiment with the Rubik's Cube, of course, is very visual, it's very helpful, but we can do essentially the same and fundamentally the same thing, not just with the Rubik's Cube, but identically with the geometric points. I did a diagram for you guys over here. You can see it on the right side of your screen, so you do not watch me do this drawing to save you some time. So here we still have, in each layer, I showed the points that are visible to us in yellow. Right here we have three 3 by 3 square on the bottom, 3 by 3 square in the middle, and 3 by 3 square on the top. So in this case, the exact equivalent of our experiment over here will be what? In this case, we'll pick physically this plane and this plane. Let's say this plane was selected as a suspect as a result of our weighing. For example, this plane on the right side. Then the blue plane, the equivalent will be this guy. Let's say we picked this plane in the middle plane between these two planes. This one went down, parabolically speaking. So now we have this plane that went down. And for the third weighing, let's say the equivalent of our third weighing over here with the Rubik's Cube, it will be the top plane and the bottom plane. Again, let's say it so happened that the left plane went down on the top plane. So it means this plane went down. And in this case, the three planes intersect where? They intersect precisely at this point. So the coin that is fake and heavy is this guy right here. And we understand again how we will designate the LRB path for this case. Once we pick our choices for each respective layer, we will roll through every coin in the selected layer of the Rubik's Cube, and into each coin that sits in the specific unit cube, we will drop the corresponding layer for weighing number 1 in the position number 1. LLL, LLL, and so on. We will roll through the second layer of the Rubik's Cube for weighing number 1. In the first position, we'll drop in the letter RRR, and so on for the remaining, for all 9 points. And we will do the same thing for the weighing number 2, except that this time we will drop in the letters R and L into the middle position, and we will do the same for the cubes that represent the third weighing for the top layer and the bottom, except that this case we'll be dropping the letters L, R, and B into the final, and in my case, leftmost position. In your case, it will be the rightmost position. But that is how we will distribute the letters L, R, B over the entire Rubik's Cube. Once we do that, we sprinkle the numbers 1 through 27, or the names of the heavy suspects, the names of the coins, in technically any which way we want. And then we take these numbers and we write down the 3 weighings. We generate a non-adaptive solution of the 27 coin problem, purely geometrically, as we explained. And now this will be the end of the second problem that we will solve geometrically. When we look at this diagram over here, what other image comes to mind? What is going on over here? Yes, technically we have 27 points for 27 points. But what else is going on here? Well, technically this is a cube that is comprised of how many, let's say, smaller unit cubes? Well, we have 4 on the bottom, 4 on the top, so we will have 8. And 8 is also what? 8 is a perfect cube, but this time instead of raising instead of raising the number 3 to the third power, here we raise number 2 to the third power. And what kind of ideas this gives us? Well, in the next and final segment of this episode, I'll share with you my idea, or my wording, of a fake coin detection problem that can fit this specific scenario. For our final problem that we will solve geometrically, we will consider the case of 8 coins, and 8 is a perfect cube when the number 2 is raised to the third power. And the number 2 tells us that instead of traditional 3 choices that we had in all the previous fake coin detection problems, parabolically speaking, left, right, balance, now we have only 2 choices. So for that specific scenario, now we need to design its own dedicated problem, or in some sense we have to fit the numbers into a given problem. And again, here is my idea. I'm pretty sure that as soon as you hear my wording, you will be able to come up with something even more beautiful and more elegant. But here is my setup. In this problem, we given 8 visually indistinguishable points. We know ahead of time that precisely 1 coin is fake and it weighs detectably more than a genuine coin. In other words, the fake coin is heavy, is designated with the letter H. And this specific set of pen scales is somewhat delicate, and it can only handle at most 2 coins per pen. The moment we put more than 2 coins per pen, this set of scales breaks down. So we can put 0, 1, or 2 coins per pen at the most, and this is our limitation. And if that is not enough, when the weighings are conducted, we are not allowed to witness every such weighing, but instead a different person has access, direct access to the results of the weighing, and that person tells us only 2 units of information. When the pens balance, the person will tell us that the pens balance. And if the pens did not balance, that person will not tell us left pen went down or right pen went down. That person will simply tell us not balanced. So these constraints are captured over here. A delicate set of pen scales that cannot handle more than 2 coins per pen, plus we're not privy to the direct results of each weighing, and instead someone else, some other person is witnessing the results and doling out 2 units of information to us. B for balanced and N for not balanced. And the objective again, in no more than 3 weighings determined with absolute certainty, the identity of the fake coin. And again, we can do it. We know that this type of solution can be adaptive, non-adaptive, and such solutions can be driven algebraically and geometrically. Here we want to design the whole package. We can do all types of solutions. We want to generate an adaptive solution, a non-adaptive solution, and a geometric solution. Here, however, the good news is that fundamentally nothing really changes that much, except that instead of a ternary tree that we had in all the previous problems that we considered so far, we will have a binary tree. And if a ternary tree is a tree in which each and every node has no more than 3 children, a binary tree, as the name suggests, is a tree in which each and every node has no more than 2 children. And in this case, we know that, for example, or we suspect that the problem can be solved with 3 weighings. We represent these weighings with the nodes over here, except for the leaf nodes. And each branch in our binary tree, we label with only 2 letters that are available to us. B for the case when the pens did balance actually, and N for the case when the pens did not balance. And each such branch depicted over here will have several legs, and each leg or each edge in this graph we label with the specific letter as shown over here. And just for kicks, because this problem doesn't seem to be too sensitive compared to the problems that we solved before, as a side note again, in real time, what I did here is I solved this problem in reverse order. Literally, I wrote down the names of all the leaf nodes, again, for our shared amusement, 1, 2, 3, 4, 5, 6, 7, 8, and then I rolled backwards, or I rolled upward through the tree and came up with the assignments of the coins in this case. And this assignment in reverse order is very straightforward to generate. For example, between these 2 leaf nodes over here, let's say we designate the balanced branch that goes to the left, the not balanced branch that goes to the right, letter B, letter N. If this leaf node corresponds to the suspect number 2, which is heavy, then obviously when we put the coin number 2 on the, let's say, left pen and the control coin on the right pen, of which we have plenty at this point, then if the pens did not balance, then obviously the coin named 2 is a heavy, fake and heavy. And if the pens did balance, then obviously the coin named number 1 will be fake and heavy. Likewise, we sort out the solution for the final weighing for the coins named 3 and 4. 4 goes on the left pen, control coin goes on the right pen. No constraint is violated. At this point, we're doing no more than 2 coins. 1 is less than 2. Everything is great. And if we come over here, then we climb one step up over here. If the pens did not balance, then obviously the fight must happen between these two coins 3 and 4. If the pens did balance, that means that neither the coin 4 nor the coin 3 is under suspicion. It's only coins 1 and 2, excluding the other ones, of course. So here we weigh 4 on the left pen against 3 on the right pen. But the more you work with this problem, the more you realize that these assignments to the left and to the right pen are really not that important. And we climb up again all the way to the top, to the root node. We see that if under this branch over here live the coins named 1, 2, 3, 4, and under that branch we designate the situations when the pens balance, it means that for the root node that represents the very first weighing, none of the coins can be on the pens. They sit out the first weighing over here on the table is shown on your right, 1, 2, 3, 4, and consequently when we work out in reverse order the structure and the names of the coins all the way back, so we come here to the distribution of coins, let's say for example 5, 6, and 7, 8. Then again, underneath for your convenience over here, I wrote down all the fates, all the unique fates or all the unique paths. In this case, these are 3 permutations with repetitions, but instead of 3 distinct items, we have only 2 distinct items, each of which is available in an infinite supply. These distinct items are the letters B and the letters N, so we have our favorite 3 permutations with repetitions of the letters N and B. This is their complete set. We also, in some sense, have a nice vehicle for visualizing, again, this combinatorial object, to which we refer as 3 permutation of 2 distinct items with repetitions. And now we understand how an adaptive solution of this problem can be generated. It's portrayed over here. Consequently, we can also write down the corresponding non-adaptive solution. We can write down the names of the coins. For example, here, for the first weighing, we will have the coins 5, 6 on the left pen, the coins named 7, 8 on the right pen, and so on. Now that we step forward, we think, okay, how can we generate a geometric solution or geometrically driven non-adaptive solution of this problem? Well, here in this case, we will also go back to the Rubik's Cube, but this time instead of a 3x3 Rubik's Cube, we will take a, let's say, 2x2 Rubik's Cube. And again, here I portrayed it with chalk to show that such a 2x2 Rubik's Cube is comprised of 8 smaller, let's say, unit cubes. And again, for a geometrically driven non-adaptive solution of this problem, what we can do is we can drop a coin into each unit cube, again, completely arbitrarily, any which way we like. For example, for demonstration purposes, I named the unit cubes of this 2x2 Rubik's Cube as follows. The upper left cube is named 1. We drop the coin, for example, name number 1 into it. The upper right cube is 2. The bottom right cube is 3. The bottom left cube is 4. Let's say, for example, this funny letter over here designates the upper left unit cube. So the way I numbered the cubes as follows: 1, 2, 3, 4 in a clockwise fashion. Then on the side, through the back face of this 2x2 cube, I put the names 5 on the top, 6 on the bottom. This will correspond to these guys, this and this. In the let's say in this plane it will be 5 and this will be 6, and consequently the very far top cube I named 7, and the bottom cube in the bottom layer I named as 8. So in our notation over here, this will be number 7 cube, number 7, this will be number 8, like so. And again, we designate the 3 weighings that we had captured with our binary tree on your right with specific faces of our 2x2 cube. This representation will be slightly different from the representation of the weighings that we had in the previous two problems. But for demonstration purposes, let's say for the very first weighing, we will pick this face of the cube, let's say the front face of the cube, and when this diagram is done slightly more professionally with the free software called GeoGebra, then that diagram will look as follows. Very well, let us agree that for the second weighing, we will pick the right face of that cube, or for example, in this representation of the Rubik cube, if this is the front face, we will pick this face right here, this guy, this face. So in other words, this entire face will be representing the weighing number 2, the face that contains the coins 2, 3, 5, and 6. Again, done slightly more professionally with the free software called GeoGebra. That representation of the weighing number 2 will look as follows. Lastly, let us agree that the third and the final weighing in this problem will be represented by the very top layer, or this entire layer right here, containing the coins named 1, 2, 5, and 7. And in our representation, in our model of this 2x2 Rubik's Cube, it will be this guy, the top layer, and done more professionally with the free software called GeoGebra, that third weighing will be represented as follows. Now that we understand what type of choices we have made, we understand also where this is going. We remember that in Euclidean geometry, 3 distinct non-parallel planes intersect at a point, and here we've essentially picked just such 3 distinct not parallel planes: the plane of the front face, the plane of the right face, and the plane of the top face. So we see where this is going. For example, under all the best of circumstances, these 3 planes will intersect at this cube over here, for example, the cube named number 2, just as a sample. But now that we made these selections for representations of the weighings, we construct our geometrically driven non-adaptive solution of this specific 8-coin problem as follows. From the front face, which is loaded with the coins numbered named 1, 2, 3, and 4, we put the coins named, for example, 1 and 2 onto the left pan. We put the coins named 3 and 4 onto the right pan, and we keep the coins named 5, 6, 7, and 8 on the table. For the weighing number 2, we go to our previously chosen face, and from that face we pick, for example, the coins named number 2 and 3. We put them on the left pan. The coins named 5 and 6 go onto the right pan, and the remaining coins named 1, 4, 7, 8 stay on the table. For the final weighing, we pick the coins from the top plane. For example, we put the coins named 1 and 2 onto the left pan. We name the coins 7 and 5 here onto the right pan, and the remaining coins named 3, 4, 6, 8 we put on the table. And now that we have constructed this solution, we need to compile the translation table so that we can generate a nice and fairly concise non-adaptive solution of this problem, instead of writing down all these 3 permutations with repetitions. And the way we construct this table shown over here, not to be confused with the assignments shown over here, this is different. This translation table corresponds to these specific choices. If you make different choices, for example, you can pick the left side of this Rubik's Cube, then you can pick the back side and the bottom, so your assignment will be different, but essentially fundamentally it doesn't matter. For these specific choices, this is the translation table that we construct. Again, we give someone the list of instructions that are written down ahead of time before the first weighing commences, and that person will simply observe the results, write them down, give it to us, and then we will take this 3 permutation with repetitions and we will convert it into a specific name of the fake coin that is heavy, and it works as follows. Let's do one such analysis together. For example, let's say as the result of the first weighing, the pans did not balance. As the result of the second weighing, the pans did balance. As the result of the third weighing, the pans again did not balance. So we describe this particular outcome with the letters N, B, N. And what does that mean? Okay, if on the as a result of the first weighing, the pans did not balance, that means that the fake coin, the suspect coin, was somewhere on the pans. The coins named 5, 6, 7, 8 are out of the question. It can be only 1, 2, 3, and 4. Now, as a result of the second weighing, the pans did balance. So that means that the coins that are on the pans are out of suspicion, and the only coins under suspicions are the ones on the table. On the table, which coins do we have? We have the coins named 1, 4, 7, 8 on the table. And what is the intersection of these two sets? 1, 4, 7, 8 and 1, 2, 3, 4. By the looks of it, the intersection of these two sets are the coins named 1 and 4. Beautiful. As a result of the third weighing, the pans did not balance. That corresponds to the letter N, and that means that the fake coin cannot possibly on the table. That fake coin can be only on the pans. And what do we have on the pans that intersects with this set over here, 1, 4? Well, that's precisely the coin number 1. And that is how we construct the translation for the coin number 1 and BN. Again, we interpret, or I interpret, these permutations right to left. You will most likely interpret them left to right. Fundamentally, that makes no difference as long as we're consistent. Now that we understand how a geometrically driven non-adaptive solution of this fake coin detection problem can be done, you can try different scenarios, pick different planes, pick different faces, play with the Rubik's Cube, and as an informal homework assignment, try to take this adaptive solution of this coin and generate over here. I left some space for you. Write down the corresponding non-adaptive solution of this problem. But for this episode, this is it for the geometrically driven solutions of the fake coin detection problems. For our next challenge, we'll take a little bit of a break from studying the dedicated problem-solving approaches. We'll look at a little bit of grown-up and more academically oriented material. As the challenge S2M17, it will be a problem in mathematics. You are invited to decompose the logarithm of the gamma function on the subset of real numbers from 0 to 1. This interval is actually open. It's closed and open. It's closed on the one side, open on the 0 side. But again, as a challenge, you are invited to decompose the logarithm of the gamma function on this subset of real numbers into its Fourier series. And as a number of intermediate tasks, for example, you should try your hand at proving the so-called reflection formula for the gamma function shown over here that holds for all, let's say, real numbers that are not integers. And as another subtask, you should try your hand at summing this particular trigonometric infinite series. And here, ideally, you want to find a more or less generic miniature industrial strength method for coming up with the sums of this trigonometric series. There will be more intermediate results that are needed for this specific task. We will look at them later. For example, we will need the result that is known in mathematical or in real analysis as the Frullani integrals, and maybe I'll dedicate an episode to the deductions and the proof for them. But for now, we'll just concentrate on these two, and we will take the Frullani integrals for granted for now. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next several episodes where we will discuss the solution of the problem S2 and 17.